Good morning. We are moving right along through chapter 21, and we have moved into this new section. So we said we are ready to take a look at distributions of charge other than just point charges. Point charges were our kind of starting point. We had formulas that work really well for point charges. Now we want to take what we've developed for the use of calculating electric fields of point charges and apply them to any charge distribution at all. So we can use that to generalize. Now we call this a continuous charge distribution. That's kind of the name this goes by. And we said that this involves carrying out integral calculations. Let's take a look at the formulas that we had talked about at the end of the last lecture. And we said, okay, here's a point charge. Here is a continuous distribution of charge. For the point charge, we had a formula. kq over r squared told us how large the electric field would be, what is its magnitude. And then this unit vector kept track of direction. Now when we moved on to a non-point charge, we said, okay, we can still treat this as just a bunch of point charges all lined up. So we could move from one point charge to the next and determine how much electric field each one of the individual locations is contributing. Now that means we take the formula for a point charge and we adapt it. We shrink down the electric field to where it's just an infinitesimal, and we shrink down the charge to where that's also an infinitesimal, and then we're done. The k is unaffected, that's just the force constant. The distances are still finite. Those are not infinitesimal, but the amount of charge and the electric field being generated, that's the relationship that we want to maintain in this formula. Now, we showed that if I start from these point charges here, in general, we can have 2 or even 3 components of the electric field that we have to keep track of. And there's an important question we have to ask ourselves in all these examples. And that is, as I move from dq to dq to dq, as I move along the length of that charge distribution, what's changing? So in this case, the dq's look like they're all kind of the same, but when I move along here, the distance is changing. So r is not a constant. R is going to have to be integrated. Not only is r variable, but the thetas are variable. Once we take the vector equation and separate it into components, now we have 2 separate integrations that have to be carried out. And they have factors of cosine and sine to them. And as we move along that distribution of charge, theta is changing as well as r. So this is kind of our starting point. Now, in order to make this integration work, I need to find one variable of integration. I need one variable that changes as I move along here. That variable could be, I could put everything in terms of theta. So maybe the distances could be written in terms of theta, or I could do everything in terms of r. And then the thetas would have to be written in terms of r. I got to find that one variable that I want to work in terms of. And often, there's some flexibility here. It's not just one method. You guys know this from your calculus classes. We can use different variables of integration to solve the same problem. So let's take a look at our first example. Now the first example we have here is a ring of charge. So the idea is that's a circle. It's flipped a little bit, so it's a circular shape with a fixed radius, and that radius is a, little a, and that's a common symbol that we use for a fixed radius. So little a is pretty common. I'm going to be using that a bunch. What we've done is we've oriented that around a central axis, and we've called that the x direction. And in particular in this problem, we're saying that measured from the center of the circle out to point, well, they're calling it point P. I'm going to be calling that point A, right? So that's going to be point A. There's an angle defined. There's a distance, little r, defined. And what we're going to do in terms of integrating charge, we're always looking for where is the charge integration. Well, that's going around the circle. So there's these little elements of dl, and those little elements of dl will take us around the circle. Now, it turns out for this example, we're not really going to use dl. So we'll see that we don't have to use that, but that's a common way to think about setting this up. If I think about that as a little bit of charge, so I actually want to write that as dq. A little bit of charge right there, dq, is generating at point P a little bit of electric field, dE. Now that electric field is going to have two components to it. It's going to have a component along the x direction and a component along the y direction. Now along the x direction, that's going to be dE with a cosine theta factor multiplied onto that. The perpendicular direction, the y direction, here's what's going to happen. As I loop, as I follow the circular path around the axis, these dE perpendiculars are going to cancel each other out. For every little bit of charge here that generates a field down at that angle, there's going to be a corresponding piece of charge exactly on the opposite side that generates an electric field in kind of angled oppositely. Now, the x components continuously add together. All of the x components will add together as we integrate along that loop of charge. But the lateral components, the perpendicular components, they're going to cancel out, because I've got E fields that are of equal magnitude pointing in all possible directions. So we don't have to calculate that. That dE perpendicular from the diagram is going to cancel out. It's going to be nothing. So when we get through, at the end of the day, our electric field, we already know. There's enough symmetry in the diagram. We know the electric field is pointing directly along the x-axis. And we know that we can calculate that by taking dE and giving it a factor of cosine theta. It's only the cosine theta component that's going to be included in this. So that's the plan. We want to integrate that expression. So let's see how to carry that out. So I hope this picture looks kind of the same as you would expect. I changed point P to point A. I kept little a as the radius. I tend to use ds instead of dl. I think ds is more common in your calculus classes, is that right? I prefer that. dq, but I want to emphasize that there's a little bit of charge here, it's dq. So here's the plan. The total electric field, we've identified, it's going to be along the x-axis. It's dE cosine theta, and the dE is going to be k dq over r squared. So I substituted that in. Now, I started bringing out everything that was constant. And you guys know from carrying out integrations, it's great to find something that's constant because I don't have to deal with that. A constant variable or a constant quantity just comes right out of the integration sign. And then we see what's left, and we have to integrate whatever's left. So in this case, well, the little k always comes out. That's just a physical constant. It turns out that as we go around that circle, little r is not changing. The distance, even though we have a distribution of charge following this circle, from a point on the axis back to any location on that circle, it's the same value of little r. That's a constant. That actually comes out the integration. I don't have to integrate that. The angle theta is also staying constant as well. I don't have to integrate that. Everything came out of the integration sign except for dq. Now what that's telling me is each dq all the way around makes an equal contribution to the electric field dE cosine theta. And so I don't have to integrate over ds. I can just add up all of the q's. So I added all the q's together, and surprisingly enough, it equals the total charge. So this integration was, it's actually a little tricky, I think, the fact that we can just add up the dq's, but once we recognize that, this integration becomes kind of trivial, because I then can just add up all the dq's, get a factor of q, and that's it. That's the answer right there. The E field is going to be kq cosine theta over r squared. Now, what we really would like, this is in terms of r and theta. For our answer, we'd like to put that all in terms of one variable, and the variable we're interested in is x. What I want to be able to tell people from solving this problem is, if I move along the axis that runs through this circular distribution of charge, if I define x equals 0 as the center of the circle, and I measure distances along the axis in terms of x, as I move farther and farther away, what's the electric field going to be? Basically, what is the electric field as a function of x along the axis? Now, I know a couple things up front. Here's what I'm guessing. If I pick a point right where x equals 0, right at the center, what is the electric field going to be? And what I hope you're all thinking is, hey, electric fields are vectors, and if I take a bunch of vectors pointing exactly opposite each other, I'm going to get complete cancellation at the center. The electric field at the center had better be 0. Now, as I move away from x equals 0, what's going to happen is, now I'm not going to get cancellation, and the electric field is going to be non-zero. In fact, I'm expecting it will grow. So as I move away from the center, I'm going to get less and less cancellation. I'm going to get a stronger and stronger electric field along the axis. But that can't go on forever. Once I move far enough along the axis, the electric field's got to drop off. I'm getting farther and farther away from the charges. So there's two offsetting effects. There's an effect of cancellation. How much of the electric field is canceling out? And then there's a distance effect. As I get farther and farther away, the electric field's got to drop off. So right at the center, the cancellation effect gives me a 0. As I get farther and farther away, well, the E field's got to drop off to 0 in that direction too. So those are two things I can check. Those are things when I finish my calculations, I can check and see if the results make sense. So let's try that. I took the formula and I replaced the little r and the theta so that everything is in terms of x and little a. So first of all, I recognize that cosine theta is x over r, so I made that substitution. And then I recognize that r is a squared plus x squared square root. And so that also can be substituted so that I have, there's my answer right there. So now I've got kqx over a squared plus x squared to the 3/2. Now there's a lot of 3/2 powers. You'll see these in other formulas. And that's always going to happen anytime we have a cosine or a sine factor. It brings in an extra factor of x over r or a over r, and it gives us a factor of 3/2 in the denominator. So don't get confused by that. That shows up in a lot of these formulas. So this is the formula we get, and we said there were a couple things we wanted to check right away. One of those things was, hey, when x is equal to 0, is the E field predicted to be 0? Because that's got to be the case, and it works. When x is equal to 0, E is equal to 0. Now, the other thing we can check is when x gets really, really, really big, as x goes off to infinity and beyond, what is going to happen to the electric field? And, remembering some ideas from calculus, I guess, as x gets really, really big, it's going to be, a squared is going to become negligible. If I put a really big number next to a really small number and I add or subtract them, once the really, really big number gets really, 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 really big, I can start to ignore that smaller one. So I'll do that. I'll just ignore the a squared. That means that x squared to the 3/2 becomes x to the 3rd. And that means that this formula becomes kq over x squared. Hey, that's a point charge. So this first problem is saying, look, as we get far and far away from this ring, its electric field looks more and more like a point charge. And that's a common feature of all the electric fields that we calculate. No matter what the shape is, no matter what the distribution is, if you get far enough away from any distribution of electric charge, it just starts to look like a point charge, which makes sense once you get far enough away. And that's what's happening in that formula. Now, I sketched out a graph of what this formula looks like. And complete cancellation at the center. And then as that cancellation effect goes away, the electric field gets bigger and bigger, but then the distance effect kicks in and the electric field drops back off again. We could take a derivative of this, set it equal to 0, and find out exactly the location where my electric field maximizes. I should have included that. I wish I had of right now. But that would, that'd be kind of interesting to go in and find out what value of x is this. Okay. So I wrote a couple of things over here. I ended up not using them. The total charge here is q. The circumference is 2 pi a, and I wrote down the circumference because I was expecting to carry out an integration all the way around that would have had a circumference of 2 pi a. And then I also wrote down this value of charge per length. We're going to see this showing up more and more in problems. Often, instead of working in terms of the total charge, we work in terms of a charge density or a charge per length. And the charge per length, lambda, in this case, would be the total charge divided by the total circumference. Again, I didn't end up using it in this problem, but in future problems, we will. So watch for that. But yeah, that all seemed to work pretty well. All right. Now we're going to move on to example 2110. I know there's so much writing on these, but let's go through this and kind of outline what they're getting at. Remember that ring we just solved for? And we solved for the electric field along the axis. What if we now took a small positive charge and we placed it at the center of that ring? And then we make sure that the positive charge can only travel along the x-axis. So going back and looking at this picture. So it's kind of like we're going to put a charge right there at the center. And maybe it's instead of a point charge, it's a little loop or something, and we have a wire. And so there's a point charge, or a loopy charge, that can move back and forth, but it has to stay on the x-axis. It can't go off the x-axis. What would happen if we move that charge off-centered just a little bit? What if we move it off to the side? We know it right at the center. The electric field is going to be 0, but what happens if we move it off to the side a little bit? And then we're going to do that and ask what happens if it's a positive charge. And then what happens if it's a negative charge? Now the ring itself is negative. So I need to include that effect. Let's see. This is the ring, but I've flipped it sideways. So this is totally a side view. And we're told now that the ring is negatively charged. So here's this circle. It's negatively charged. Here is a little positive point charge. The positive point charge can only move along the x-axis. It's attached to something, a little rail there that means that it can only go back and forth. Has certain mass, has certain charge. That's going to be attracted to the ring. So what would happen in this case is if I move it a little bit away and let go, what it's going to do is it's going to be a force that pulls it back to the center. But when it comes back to the center, it's going to be moving at some speed. It's going to overshoot. And what we expect then is it will go into oscillations. Now, this is kind of one of those idealized physics, let's think about what would happen here sort of problems. And so what we've got is a point charge that if there's no friction, for example, it's sliding along some kind of a rail, there's no friction, and so it would oscillate back and forth along the axis of that circle. Now, let's take a look at what happens if the point charge is negative. So we're going to keep the same ring. The ring is still going to be negatively charged. Now, the point charge itself is negative. What happens in this case? Exactly. So the negative ring and the negative point charge repel. They push away from each other. So that means that this charge then is going to be pushed away from the ring. It's not coming back. This is what's considered a stable equilibrium. There's an equilibrium point right at the center where if I place it really, really carefully right at the center, it just stays there. Now, in this case, if it gets nudged, if it gets pushed just a little bit off of the center, it's going to come back, and then it will oscillate back and forth. That's a stable equilibrium point. A stable equilibrium point says that if there is a displacement, that there will be a restoring force. Now, I'm hoping this sounds familiar from chapter 14, I think, from Physics 4a. Chapter 14 was all about oscillatory motion, and we said that oscillatory motion occurs when we have an equilibrium location, and if the object is pushed away from equilibrium, there are forces, restoring forces, that will bring it back to equilibrium, and that's what we've got here. Now, in this case, it's an unstable equilibrium, right? This is like trying to balance a pencil on its point, where if I balance that charge right at the center perfectly, there's no force, but what happens if it just barely goes to one side? Then there's not a restoring force. There's a repulsive force that pushes the objects away from each other. So at the center would be an equilibrium point for both positive and negative charges. This would be stable and produce the oscillations. This would be unstable and would result in the object being pushed away. Okay, so that's kind of, it's a good example of how to determine, are we going to have oscillatory motion with a stable equilibrium, or are we going to have something that's unstable so the two objects just separate from each other. Now, for the oscillations, let's go in and take a look at this a little more carefully. For the oscillations, we can actually ask, is there a way we could determine how much restoring force there will be? And again, going back to chapter 14, I know that's asking a lot to go back to Physics 4a and remember chapter 14, but we're going to try that. What's the frequency of oscillations? Because back in 14, we had become experts at identifying oscillatory situations, which we've already done. And then once we've identified that, calculating the restoring force in a way that we could determine frequencies. So back there in chapter 14, it was 14, the frequency in radians per second depended on a force constant and the mass of the object, and we could take that ratio and then square root it, and that would give us the frequency. And we had shown that for simple harmonic motion, oscillatory motion that looks like a sine or a cosine, this calculation could be carried out. Now, we already have way too many little k's. We had little k's that were spring constants. We had little k's that were Boltzmann's constant. We now have little k's that are electric force constant. So we got to keep the k's straight. So k, the force constant k, is the relationship between force and displacement. Now, the force that we're going to have here is equal to negative q times E. That's how much force a charge q would have an electric field E. And what we had calculated was that going back to example 21.9, the electric field is going to be given by this expression right here. kq times x over a squared plus x squared to the 3/2. That's the electric field. So coming forward, I took that expression and substituted that in. So the little k here is the electromagnetic force constant, or the electric force constant. And I now have that extra factor of little q. That's the charge of this small object that we brought in. And then I also wrote down the mass. We're going to need to know the mass of that in order to determine what its frequency of oscillation is. Okay, that mass is going to go in right here. Let's see. To get simple harmonic motion, we can keep the displacements small. So in general, it won't be simple harmonic motion. The oscillatory motion could be a more complicated function. But let's go ahead and just solve for small displacements. And small displacements would say that x is much, much less than a. So again, what we can do with a side-by-side comparison of something that's added or subtracted, if a is much, 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 much larger than x, if x is small compared with the radius, then we can ignore the x's on the bottom because the a squared will dominate. So when we do that, the denominator becomes a to the 3rd, and now we have a force, a restoring force. There's a minus sign right there because if the displacement is positive, if x is positive, F is going to be in the negative direction. If the displacement x is in the negative direction, F is going to be in the positive direction, and that's our definition for a restoring force. So I put that minus sign in to say, yeah, from my diagram I can see that it's a restoring force. And the force constant, this K constant, turns out to be electric force constant times the product of the charges divided by a to the 3rd. And I can substitute all of that in. That tells me what the frequency of oscillation is going to be. So maybe we build a device. So you guys are all engineers, right? We build some kind of a switching device or whatever. We put a little tiny ring inside there that can be charged, and then we have a small charge within that, and that small charge within there is oscillating back and forth, and depending on how much mass it has and the two charges and the radius of the ring, we can build that in a way where we'll have a known frequency of oscillation. Maybe we can change the charge. As the charge increases, the frequency of oscillation goes up. As we reduce the charge on the ring, the frequency of oscillation goes down. Okay, so these are the kind of things you can start thinking about in terms of, what kind of devices could we make that would utilize what we're learning about the electric force. All right, questions on that? Very good. And chapter 21 goes on and on and on, right? So we've got more coming up on this chapter. All right. let's try another example. This one's probably a bit more challenging. We just keep stepping this up, right? So what this one is saying is, look, if we had a long continuous line of charge, a long line of charge. Now by long line, they mean it goes on and on and on and on. Now in reality, we don't have infinitely long lines of charge. Instead, what we have is measuring the electric field very close to a finite length. So let's say that the entire length of charge is only this long. But instead of having point P way out here, what if we bring it into here where it's very close to the line of charge? Well, it turns out that if we identify a point in here, just outside the line of charge, to calculate the electric field, that it's as if the electric field we calculate is going to be the same calculation as if the line of charge was infinitely long. It turns out that if we're really close to a finite line of charge, that when we carry out the integration, we might as well just imagine the integration goes off to infinity, because these outer regions end up not contributing substantially. So we can use this as a bit of an approximation. All right, so, and here is lambda. So this is the charge per unit length. We introduced that a couple slides back, and now we're going to make use of that. Now, if I have a line of charge, and I pick a point that is symmetric, and by symmetric I mean, this distance here matches the distance over here. Well, that says as I move along the line of charge, these lateral components, the y components, will cancel out. Because every time I have a little bit of charge here, I got to go back and edit these a bit. There should be a little dq here always. So that's, not only is that dy, it's also dq. There's a certain amount of charge right there. I know they're working in terms of lambda, but I always feel like it's good to tell myself there's a little bit of charge here, a little bit of charge here, a little bit of charge here. And there's going to be another piece right here with an electric field that is the mirror image of what we have here. And that means the EYs will cancel, but the DEXs will keep reinforcing each other. Okay, so those are things to keep in mind. We'll come back to this picture. The picture is handy because it's so well drawn. That distance is x. This is what we're calling r, which is x squared plus y squared. Let's see how I've tried to solve for this. Okay, I changed a couple things in here. I hope you guys are okay with this. What I did was, instead of doing a section here and a section here, I just isolated one section. I said, let's go ahead and pick a certain length, and I called that length A. Now, what they called X on the previous page, I called that B, and the reason I did that is, sometimes when I see X in there as a constant value, I get confused. To me, X is a variable. I have to kind of remind myself in some of these problems, X is no longer a variable. X is, it's fixed, so I can treat it as a constant, and that's important when I'm doing integrations, because when I'm doing integrations, you guys know, the tricky part of this is identifying what's my variable and which are the constants. So anyway, I changed this to B. I went back and edited it actually. Changed that into B. There's a little bit of charge here, and it represents a little bit of length, dy. And there is r right there, and r is equal to y squared plus b squared to the half, right? I have a right triangle. So I'm getting everything set up here. Now, the way I've set this up, both of these components are going to be non-zero. There's not going to be a cancellation. I didn't make it symmetric. So I need to calculate an overall EX, and the EX will come from this. Here we go. So the k dq over r squared, that's what we've been using. for the infinitesimal electric field. And the cosine theta component is going to be along the x direction. The sine theta component is going to be along the y direction. Now, I'm going to do that on the next page. So this page is now all about calculating EX. See, I have it written here. Here's EY, here's EX, here's total E, and the EX is going to have that factor of cosine theta attached, and the EY component is going to have a factor of sine theta attached to it. All right, so EX is, okay, we got to talk about how do I deal with DQ. So DQ works this way. Total Q would be the total Q of the entire length. So a little bit of Q is going to equal the total charge divided by the total length times a little bit of Y. It's a ratio thing. Down in the parentheses there, it says that if the charge is uniformly distributed along the length, then if I pick some arbitrary little piece of length, the dq is to the total charge as the little bit of length is to the total length. So dq is to q as dy is to a, and what that enables me to do is write down an expression to substitute in for dq. Remember, this is doing an integral, and I have to get everything in terms of one variable of integration so that I can carry out the integration. And so that's my substitution for dq. Now, once I've done that substitution, I did this one also. Cosine theta needs to get re-expressed in terms of y. And so cosine of theta is going to be b over r. I made that substitution. And then finally, little r, the distance, is going to be y squared plus b squared to the half. So I substituted for dq. I had to carefully identify an algebraic expression for dq. I had to write down the expression for cosine theta, and then I wrote down the expression for r. Once I had made all those substitutions, I then pulled out some of the I didn't pull out b. I'm not sure why I left it there, but I did for some reason. Anyway, the little b could have come out too. So I was left with k cubed b over a. And then what's left in the integration sign is dy over b squared plus y squared to the 3/2. Now that's a difficult integral. So I didn't solve that on my own. I looked in the appendix. In the appendix of our textbook, there is, I think it's Appendix A, there's a bunch of math formulas, and there's a section back in that appendix that has commonly used integrals. So, it's fine to, kind of challenge yourself and say, can I solve that integral? But a lot of times in physics or in engineering, we just decide, I'm just going to look this one up. And then maybe I verify it. But I looked this one up, and it said that, and again, the b should be out here, it said that that integral is y over b squared, y squared plus b squared to the 1/2. So I went to Appendix A, looked up that integral, and then I wrote down the integral right here. Now, the limits of integration are that y goes from 0 all the way to y equals a. So notice I set up a coordinate system where the center of the coordinate system is right here at that junction. And that turned out to be convenient because point A is right along the x-axis and the line of charge is right along the y-axis. So that worked out really well. All right, in my coordinate system. So that kept all these expressions as simple as possible. And then this also, the 0, a, it kept the limits of my integration as simple as possible. Now, when you do integrations, there's two approaches. you can put limits of integration and build those right into your calculation, or you can solve indefinitely and get a constant of integration and evaluate that after. Use the first method, don't use the second one. In physics and in applications like this, almost always, I'm going to say close to 100% of the time, it is highly, highly advised, establish what your limits of integration will be. Going back and evaluating a constant of integration can be a real bother. So let's get the limits of integration established, and that would be values. We want to include values of y between 0 and a. So that's what we've done here. I looked up the integral, evaluated it between 0 and a. This is what it became when I substituted that in. At the limit a, I substituted a in for the y's. At 0, it went to 0. So I didn't have to write that one down, and that's my formula. Now I got some cancellation here. I got a couple a's to cancel. Up here I had a b and a b squared, and one of those canceled. And this is my final expression. So this is it. I calculated what is the x component of the electric field due to a section of linear charge that's all lined up along the y-axis with this particular orientation. And that's the formula I got. Now, what would I do then if, in order to calculate the electric field, if I put a second section in here? Well, if I put a second section in here, that would double the charge. So I would have to double the charge that was here. And then I would have twice as much electric field. So I would have this much charge, or this much electric field due to this much charge, and then I would get an additional portion due to the charge that's down here. And so actually the formula would look the same. I would have twice as much charge, and it would give me twice as much electric field. Okay, so we can now piece together different lengths in order to get any length of charge that we want. Let me see if I've got a follow-up. I do. So let me go back here. So at the end of this, what we've gotten is we've calculated this component. Now let's calculate the y component. Now there's just a lot of similarity here. So very same integral, except this time it's sine theta instead of cosine theta. And so the sine theta expression is going to be y over a. So I substituted those in. The limits of integration is still 0 to a. I looked up that integral. That integral is different than the one we saw before. This one has a factor of y here that the other one did not have. Same appendix, in fact the two integrals are right next to each other. They're common integrals that we have to carry out for calculating electric fields. This shows up pretty frequently. So I looked at the limits, 0 to a, and this time I didn't get a 0 at either limit, so I had to keep this expression. So there they are. There are the two components, the x component and the y component. Again, referring back to the diagram, I've got this line of charge. I pick a point, some distance b out here, and the length here is a. I'm going to have an electric field component x, electric field component y. And these are what the two components are given by. Okay. Now what we want to do is this. What we want to do is consider a very long line of charge. What we're going to do is let a go to infinity. We're going to ask, what do these integrals give us in the limit where a goes to infinity, and we also double up. we do an integral here and an integral here. And so the electric field we're going to get is 2 times the formula that we had before. It's going to be 2kq over b, 1 over a squared plus b squared to the half. I've got to think about that some more. And then the limit as a goes off to infinity, what's going to happen there is that as a gets really, really big, I can begin to ignore the b squared in a squared plus b squared because it's added. If it's added, then this number is getting really big and we're going to add this tiny number to it and it's going to be negligible. Now I can't ignore a factor of b. A tiny factor has to be included. That's not going to go away. But as a gets really big and it's added with b squared, the b squared portion can be eliminated. So this became 2kq over ab. Now that's the formula I got for the E field, so that's it. We've solved this. And it has, the form to it corresponds to, the form that we've come up here has the right set of units. It's a kq over 2 distances. Now the problem I have with this E field formula is when a goes to 0, as a goes to infinity, the electric field goes to 0. Now that doesn't make sense. Why is my formula doing that? And that's because I wrote it in terms of the total charge. If I have a line of charge that is infinitely long, but it has a finite amount of charge, that means that the charge is just spread out so thinly that it basically has no E field at all. So I've got to go back and do something different. What we can do is say that there is there's a lambda, there's a charge per length, and that would be equal to q over a. So what we had identified was q was just this half, and there's a second amount of q over here. And so lambda is going to be q divided by a. I can make that substitution, and now I've got an E field that's 2k lambda over b. So the idea now is I'm going to maintain the same charge per length. If I let a get really, really big, well, q gets really, really big too. And both a and q grow proportionally so that now I can calculate an E field. Now my formula is going to be workable because it's in terms of the charge per length. So this is it, 2k lambda, charge per length, divided by b. Now, once we've finished the problem, I'm going to take b and turn it back into a variable. I'm going to go, I solved the problem for one particular distance b, but now I want to let b be a variable. And so this formula tells me as long as I'm at some distance away from the line of charge, so that b is very small, or little r is very small compared with the length, this will be a useful approximation. That's the E field surrounding this line of, or this long wire of charge. And the E field is going to be pointing away perpendicularly from that very long line of charge. All right. Okay, so a more challenging example. Questions on that? Stop by office hours, but a good example to think about. Okay, moving on to one more example. So I hope this is interesting. I know that some of these problems are challenging, but again, it's such a good example to apply the integration techniques that you've learned in your calculus classes. I hope that's kind of exciting to think, oh wow, this really applies to something. We can really go in and calculate these electric fields, carrying out these different integrations. So let's do this. Instead of a ring of charge, let's do a disk, a circular disk, uniformly charged with, say, positive charge. We'll pick a point up here, point P or point A. We're going to keep it right along the axis. That's using a lot of symmetry at this point is about the only way we're going to get these problems solved. If we pick a random point over here, the integrations are going to be too complicated for us to carry out. So it's true, we're kind of limiting ourselves, even with these more challenging problems, they're still being kind of limited to points along the axis in this case. In the diagram, they've used the z direction. When I do this, I'm going to flip this 90 degrees. I do better if I'm working along the x-axis than z. The z-axis is going to confuse me. I know that sounds ridiculous, but... and then the radius here, they're using big R. We may use big R, we may switch to using A. Now, the way this disk is going to be broken up is it's going to be broken up into a series of concentric rings. Now, I'm guessing in calculus you've done this integral. This may go back to 3A or possibly Math 3B, where you took a series of rings, infinitesimal rings, and added them together to derive the area of a circle. Okay, so we're going to do the same thing here. We're going to use that approach. Here it is, as promised. I flipped the disk, moved it along the x-axis. I picked a particular point, x, out here. I did switch over to little a. So I'm using little a as a radius. That's what they were using on some earlier examples. Little r now has become different, so I've got to be clear about what little r is being used for. Little r is telling me, as I integrate these different rings, starting at the center, working out to the circumference of the disk, little r is a variable which tells me which ring I'm looking at. Now, each one of the rings is going to have an infinitesimal piece of charge, but they're not all going to be the same. Some of these rings have more area than the others. The one near the center have very little area. The ones as we get farther and farther out have more and more area. So we need to keep that effect correctly represented, and here's how we're going to do it. So we're going to use that same ratio approach. Now, the ratio approach works real well as long as the charge density is uniform. We have a total charge of Q, and it's uniformly spread around the circle. So that says if I measure the area of a ring and compare it to the total area, that fraction will tell me how much charge is contained in that ring. So here is that ratio of approach. The dq for any individual ring compared with the total charge, Q, is equal to the area. Now I could have done this as d area. I should have put an intermediate step here of d area over area. So the d area, the area of the ring itself, is 2 pi r dr. Now that you should be familiar with from your calculus classes. Where that comes from is if I take a ring and I make it really, really thin, its inner and outer circumference are so similar, I can cut that out and treat it as if it's just a long rectangle. The thickness of that rectangle would be dr, and the length of it would be the circumference, which is 2 pi r. So the area of one of those infinitesimal rings is 2 pi r dr. Now the area of the whole circle is pi a squared. So taking those expressions and solving for dq says that each one of the rings will have some portion of the total charge, and that portion is going to be 2r dr over a squared. That's going to be my expression for dq, and notice the dq's are not the same. A dq closer to the center has very little of the charge, but a dq out along the circumference has much more. But this expression will correctly keep track of the q. Now, the other item we have to write down here is how much dE will I get from each ring? Well, we solved that problem back here in example 21.9. we solved the problem of what's the electric field due to a ring of charge. And so now, I'm going to write that expression down. That's what we solved back in example 9. And I'm going to scale it down. This was for a finite amount of charge, but now the rings that we're looking at have an infinitesimal amount of charge. Finite, infinitesimal. So a little bit of charge is going to generate a little bit of electric field. Now everything else in here stays the same. Little k doesn't change, that's a force constant. The lengths are all still finite quantities. It's just the q that becomes infinitesimal. So this is what I want to use when I'm adding together the effects, the E field contributions from all of those rings. All right, so to get the total electric field, I'll add together the dE for each one of the rings. That's going to be this expression right here, substituted into my integral. Now, that expression has a dq in it, and the dq we talked about earlier is going to be represented by this algebraic expression, and the dq is being related to dr. So dr are those little incremental steps from the little tiny rings to bigger ring to the bigger ring, bigger ring. Each ring has a width of dr as we make our way from the center out to the circumference. So I substituted this in for dq, and now my integral looks like this. 2 times k, big Q, x. Now remember, x is a constant right now. So that comes outside my integration. The variable of integration here is little r, which is giving us the radius of the circular loops of charge. So everything now is in terms of r. The x here is a constant. The r is the variable. And once again, I looked up that integration in the appendix. That's the same integral that we used in one of the previous examples. But I still didn't remember it. I had to look it up again. Now, there was a minus sign in that when I looked it up. Now, here's a trick you can use when you're evaluating these integrals. If the integral that you find has a minus sign in it, to get rid of the minus sign, you can reverse the limits. This is really handy for exponential functions. It's really handy for inverse functions. When I have some power of r, for example, in the denominator, when I carry out those integrals, I get these integrals with minus signs, and what will happen is I'll get an integral where when I evaluate it, I have a negative minus the negative of another negative. I start to lose track of minus signs. I don't know how you guys are, but it's easy for me. Once I have 2, 3, 4 minus signs, my failure rate starts to go up. So there are these little tricks that you can use to eliminate minus signs as they come up, which for me really helps. It helps me from getting a sign error. So to remove the minus sign, I reverse the limits. Now when you do that, what should happen is that the expression you come up with will now be a positive value. And it worked. So again, it works well for exponentials, it works well for inverse powers of the variable. And I got E is equal to 2kq over a squared. And then evaluating this at the limits, at the 0 limit, this became I think I might have a factor of r. No, that looks right. At the 0 limit, I've got 1 over x. Okay, I did 2 steps together. I apologize, I shouldn't have done that. At the 0 limit, I have 1 over x squared to the half, which is 1 over x. I have a factor of x here. So bringing this x back over and letting the r go to 0 leaves me with a 1. at that limit. When I put a in, I now have 1 over a squared plus x squared, and again that factor of x comes over. So I should have done that in 2 steps. So this is the expression I ended up with. Now this is a useful expression. We're going to come back and use this. This is actually something we're going to spend some time with. It turns out that a circular charged disk is a very useful way to discuss E fields around kind of any flat distribution. So a circular shape is enough symmetry that we get a fairly easy expression, I'm going to claim, to work with. And then we can play around with this function and see what it looks like. So now there's another way we could write this down. Instead of writing down the electric field in terms of total Q, so we're saying there's a total amount of Q on this disk, what we can do is a charge per area. Now, we did charge per length. Remember lambda? Well, we can also do charge per area, because this time the charge is not spread along the length, it's spread uniformly over an area. And so charge per area, for that we use sigma. We use all this Greek stuff for these charge densities. So charge per area would be Q over pi a squared, that's the area of that circle. And if I make that substitution, Q is equal to sigma pi over a squared, the a squareds cancel. And I'm left with 2 pi k sigma, which is my charge per area, times this function of x. Okay. Now, let's take a closer look at what these formulas are telling us about the electric field. So the first question I want to ask is, what happens if I come up really close to this surface? What if I come up so that I'm just right against the surface? And what happens in this case as we come up really, really close is, and here's a picture of the function itself. So I'm going to be switching back and forth between these slides. If I put x is equal to 0, let's see, here are the formulas that we just derived. If I put x equal to 0, what I'm getting now is, with x equal to 0, I get 2kq over a squared in terms of total charge, or 2 pi k sigma. So here's that charge disk. I'm doing a side view, and the E field is showing it's going away from the disk. And I'm trying to outline, estimating what the E field would look like. Now if I'm right up close to the surface, it looks like the E fields are coming directly away from the disk. But what happens as I get farther away is that disk is, I'm expecting, is going to start looking like a point charge. So is there a way we could go in and start with the formulas that we've derived and ask, well, at x equals 0, what's going to happen? What happens when I get really close to the disk? And what happens when I get really far away? Now, when we got really close to a ring, remember with the ring, when we went right to the center, we got complete cancellation. And you know what? That's what should be happening here also. But it doesn't. So how do we resolve this? There seems to be a contradiction if we get right to the center point of that disk. Well, the way the integral is set up, it's imagining that this disk is infinitely thin. We didn't include any thickness of the disk. And that says, in the limit, as x approaches 0, we still have the effect of all of that charge pushing away from us. So, in reality, if we had a charged disk, once we get to the surface of the disk, it's really, really thin. This formula works, but when we actually go into the disk and set ourselves right down at the center, the E field would cancel out. And these are the kind of dilemmas or the paradoxes or the apparent contradictions we run into. You'll see these come up from time to time when calculating electric and magnetic fields. Is built into our integrations are assumptions about the shape, which don't match up with reality. They're not really objects that are infinite in size. There are not objects that are infinitesimally thin, and that's what we're assuming here. So again, these formulas are going to work really well if the disks are really, really thin, but in reality, we're always going to be able to go into the disk, and that's where the E field would drop to 0 right at the center, but it doesn't show up in our formula. Our formula didn't take into account going within the charge distribution itself. We'll see some examples of that in the next chapter. Okay. So that limit is going to remain finite, and in fact, going back to here, this is what the formula looks like. So I plotted, oh, I didn't write it down either. I plotted this expression. See the stuff in the brackets? I plotted 1 minus x over a squared plus x squared to the 1/2. This is just a bunch of constants out front. But I wanted to see what shape this function was of x, and that's it. And what happens is that function starts out being 1 at that point, and then it drops to 80%, 60%, 40%. So that's what this axis is keeping track of. Now, x is being kept track of in terms of numbers of radiuses. So when x is equal to 0, we're right at the surface. Remember, the way we set up the integration doesn't take into account actually going inside. So it remains finite, and in fact, it's the largest value right at the surface, because we're coming right up next to a charge. In the ring case, there was no charge that we were coming up right next to. In this case, there is. And so the highest point of the electric field is right against the surface. And then this would be where x is equal to a. Let's say that the disk has a radius of 5 centimeters, a diameter of 10. So if the radius is 5 centimeters, then once I get 5 centimeters away from that disk, the electric field will have dropped to about 30%. So that's a pretty quick drop off. If we say right at the surface is the full electric field, and then 1a distance away, it's dropped down to about 30%. By the time we get out to 2 times a, we've dropped down to about 10%, and then it continues to drop off. Now, what would a point charge look like? If instead of having a disk with the charge spread out, if I had a point charge where all the charge was concentrated, and I start moving closer in towards that point charge, the E field is going to go up even faster, right? Here, once we get close to this disk, we're going to start getting some cancellation. But if it was all concentrated into a point charge, we would never get any cancellation. We would get the full effect of the entire amount of charge. So the point charge would be kq over r squared. And if I plot that on here, it rises steeply. And in fact, in that point, we have the E field goes off towards infinity. If it's a true point charge, then the E field just gets larger and larger as we approach. Now, in reality, we don't have charges that are all concentrated at one point. Even protons and electrons are going to have some size to them, some charge distribution. But that's the idea, is to do that kind of comparison. Now, we can actually do that mathematically, but I'm thinking that's probably a good place to stop for the day. I think what we're going to do is come back and spend a little bit more time on this particular example, which is very useful. So let's do that. We'll end there for today.